Imagine the most powerful, most expensive machine ever built. Rows of glowing GPUs, humming in a dark data center, burning millions of dollars every single hour. But here's what nobody puts in the brochure. Sometimes that machine just sits there, not computing, not generating, just waiting. Waiting for data that hasn't arrived yet. If you look at a real GPU monitoring screen, you might actually see this status message. GPU utilization, waiting for memory. A billion-dollar chip, doing nothing. So here's the question I want to start with today. What if AI's biggest obstacle right now isn't a smarter algorithm or a better model, but a traffic jam inside the machine? Today we're tracing the entire story, from AI's very first bottleneck, all the way to the hidden infrastructure battle reshaping trillion-dollar companies right now. This is the story of data, GPUs, a concept called the memory wall, and a Korean-made chip that may be the most strategically important component in all of modern AI. The history of AI is not just the history of smarter machines, it's the history of bottlenecks. And understanding that changes how you see everything happening in tech right now. Ready? Let's go back to the very beginning. Because to understand where AI is stuck today, you first need to understand what made it run in the first place. Go back to the early internet. People are clicking, searching, buying, watching, commenting. And somewhere in a server room, every single action is being quietly logged. Google, Facebook, Amazon, YouTube. These weren't just popular products. They were data harvesting machines collecting billions of behavioral data points every single day at unprecedented scale. You clicked on running shoes once. YouTube remembered. You watched a political video, then a cooking tutorial. Facebook logged all of it. Amazon knew what you needed before you did. In the early years of modern AI, data was the decisive advantage. More high-quality data equaled a smarter AI. Data was literally the raw material of machine intelligence. Data is the new oil. That saying was everywhere, and for a while it was basically true. Silicon Valley's biggest competitive moat wasn't code. It was a decade of hoarded data. But here's where it gets interesting. What if data is infinite was always a myth? What if there's actually a hard ceiling on the useful, quality human text available for AI training? Researchers at Epoch AI estimated the total effective stock of quality human-generated public text for AI training at around 300 trillion tokens. Sounds enormous, right? But at current growth rates, language models will fully utilize that entire stock somewhere between 2026 and 2032. The internet felt infinite, but the useful part has an expiration date. It doesn't mean AI stops. But the just feed it more data strategy has a wall, a real physical mathematical wall. The first bottleneck has a finish line, and we're approaching it. So the question changed. Okay, you have the data, now what? You need something to actually process it. You need raw computational power. You need the engine. You need GPUs. This is where NVIDIA enters the story. And its rise is one of the stranger arcs in recent business history. Because NVIDIA originally didn't build chips for AI at all, NVIDIA made GPUs for video games, rendering pixels quickly and in parallel. But AI researchers realized that same parallel architecture was perfect for training neural networks. As AI models scaled up, more parameters, more data, more complexity, compute requirements went exponential. Training the biggest models started taking weeks, even months, on specialized hardware. The computing power required to train state-of-the-art AI was growing insanely fast, doubling roughly every few months. That's not Moore's law. That's several times faster than Moore's law. AI companies started looking less like software startups and more like industrial operations. Training one large model could require hundreds of millions of dollars in computing infrastructure. Think of it this way. Data is your raw material, the ore. GPUs are your machines, the smelters and factories. All the ore in the world means nothing without the factory to process it. For a while, the formula felt almost clean. More GPUs equals better AI. NVIDIA's market value soared from tens of billions to trillions of dollars. GPU clusters became the hottest real estate in tech. But here's a quiet, uncomfortable reality that started emerging. The GPUs were getting insanely fast. Faster every year. But data still had to travel to those GPUs. And that journey had a speed limit. Imagine building the world's fastest race car, then discovering the only road it can drive on is a single-lane country road with a 30 mph speed limit. That's basically what was happening. The GPU era solved the compute problem brilliantly. But in doing so, it exposed something that had been quietly deteriorating for 30 years. Something called the memory wall. Here's a fact that sounds like a footnote but is actually the center of everything. Back in 1990, a researcher warned, memory bandwidth is not keeping up with processor speed. Then in 1995, two scientists named Wolf and McKee gave this problem a name: the memory wall. Compute speed and memory speed were diverging. They predicted it would eventually become a crisis. Nobody really fixed it. Engineers kept building faster processors and hoped memory would catch up. 3 decades went by. And then AI arrived, but Ian transformed a slow-growing problem into a full crisis. UC Berkeley researchers published a paper called AI and Memory Wall. Their finding: over 20 years, peak server computing power grew 60,000 times. Memory bandwidth? Around 100 times. 60,000 versus 100. Let that sink in for a second. That is not a gap. That is a chasm. And your AI model falls into it every single time it needs to think. More precisely, peak flops, raw computing power, doubled at roughly 3x the rate of memory bandwidth growth. DRAM only scaled 1.66 every 2 years. Interconnects, a measly 1.4x. Translation: the engine got 100 times faster. The fuel line only got 3 or 4 times wider. Every single year, your blazing fast GPU spends more of its time just waiting. There's a technical metric for this called arithmetic intensity. Calculations performed per byte loaded from memory. For AI inference, this number is dangerously, critically low. The math doesn't lie. Think of it this way. You hired 1,000 of the world's fastest chefs, but your kitchen has only one tiny service window to pass ingredients through. The chefs are all just standing around, waiting. That's your GPU cluster, an enormous, expensive, blazing fast workforce, choked by the narrow pipeline feeding it. The chefs are not the problem. The window is the problem. And this isn't just a training problem. It's an inference problem. Hitting every AI-powered response, every chatbot reply, every real-time AI decision happening billions of times daily. So the real question isn't just how to build a faster GPU anymore. It's, how do you build a wider road? How do you feed the GPU what it needs as fast as it actually needs it? Before we get to the solution, let's go one layer deeper into the problem. The distinction between training an AI and using one changes everything about where the bottleneck actually bites. Training is when you build the model. Billions of examples, hundreds of billions of parameters adjusted, weeks on thousands of GPUs. It happens once, or maybe a handful of times. Inference is what happens every time someone actually uses the AI. You ask ChatGPT a question, that's inference. Every AI tool response, every recommendation, every summary. 1 trillion times a day, globally. Training is a one-time cost. Inference is a recurring cost, paid forever for every user, every query. And as AI adoption grows, inference is where the memory problem truly becomes existential. Here's how AI actually generates text. It doesn't write the whole response at once. It predicts one token at a time, looking back at every single previous word to figure out what comes next. Every single token generation requires loading model weights from memory, consulting prior context, running the calculation, and writing output. Then repeating, for every word in the response, hundreds of times. This is precisely why inference is memory-bound, not compute-bound. The bottleneck isn't performing the math, it's moving the data fast enough to perform the math in the first place. Now let's talk about something called the KV cache, one of the most important and least understood challenges in modern AI. KV stands for key value. Stick with me, this is where it gets interesting. Every time AI processes your text, it generates key value tensors for each word, like a running memory of what it's been paying attention to. Rather than recompute this every step, it stores it in GPU memory. That KV cache grows with every word added to the conversation. Every document you feed it, every tool it calls, every step it takes. And GPU memory is not infinite, not even close. The math is brutal. A single 7 billion parameter model with a modest conversation consumes roughly 2 gigabytes for the KV cache alone. Now scale to thousands of simultaneous users. You see the problem? Have you ever hit a context limit chatting with an AI? Or noticed it slowing down during a really long conversation? That's not a software bug. That's the memory wall in real time. Now think about where AI is heading next. Not just chatbots answering questions, AI agents, systems that plan multi-step tasks, read documents, search the web, run code, and remember across sessions. An AI agent doing deep research might hold dozens of documents, hundreds of intermediate reasoning steps, and thousands of tool outputs in active memory simultaneously. The KV cache doesn't shrink. It explodes. NVIDIA has said it explicitly. In Agentic AI, the KV cache isn't just temporary working memory anymore. It becomes long-term memory, reused and maintained across entire multi-step task sequences. So now you understand the problem. A widening gap between compute speed and memory bandwidth. An AI industry that needs to move data faster than ever. This is where HBM enters the story. HBM stands for High Bandwidth Memory, and the name tells you exactly what it is. It provides the extraordinary data throughput that modern AI requires to function at commercial scale. Here's the key distinction. Regular DRAM memory is like a storage warehouse miles away, useful but slow to access. HBM is stacked physically on top of or right next to the GPU chip itself. If regular memory is a warehouse 3 blocks away, HBM is the conveyor belt running right alongside the production line. Data doesn't travel far at all, it's right there. Instantly, continuously. The bandwidth numbers are almost incomprehensible. NVIDIA's DGX B200 system delivers 1,140 gigabytes of total GPU memory and 64 terabytes per second of HBM3E bandwidth. Per unit. Second, 64 terabytes per second. That's equivalent to transferring over 12,000 full HD movies every single second. That is the highway speed modern AI infrastructure needs to actually think. NVIDIA's latest Blackwell Ultra GPU pushes this further. 288 gigabytes of HBM3E per chip and 8 terabytes per second of bandwidth. 3.6 times more memory capacity than the H100 from just a few years ago. Why does that extra capacity matter so much? Bigger memory means trillion parameter models can live entirely on chip. No offloading to slower storage, no waiting, full-speed inference at maximum scale. Now here's the geopolitical layer of this story nobody talks about enough. Who actually manufactures HBM? The answer is 3 companies, just 3, and 2 of them are South Korean SK Hynix, Samsung Electronics, and Micron Technology. That's the entire global supply chain for HBM. 3 companies controlling the memory every major AI system in the world depends on. In early 2026, SK Hynix held a 58% share of the global HBM market, with Samsung and Micron splitting most of the rest. Stop and think about what that means for geopolitical leverage. Jensen Huang, NVIDIA's CEO, flew to Seoul in June 2026. He met with the heads of South Korea's biggest tech companies, and he said plainly to reporters, memory is constrained. He also showed up with bags of chocolate chips labeled HBM chips and handed them out to Korean executives, who started chanting HBM. That's not just fun. That's a statement about power. He confirmed, Samsung, SK Hynix, and Micron are all racing to supply HBM4 for NVIDIA's next-generation Vera Rubin platform. 3 suppliers, 1 buyer, 1 race. The stakes couldn't be higher. SK Hynix, Samsung, and Micron all crossed the $1 trillion market cap within weeks of each other in 2026. The AI memory boom had transformed 3 chip makers into trillion-dollar global giants. All right, let's pump the brakes for a second. Because it would be easy to walk away thinking HBM makers are about to replace NVIDIA. That's too simple. And I'd be shortchanging you if I left it there. NVIDIA's power doesn't come from one chip. It comes from an entire integrated ecosystem. GPUs, HBM, NVLink interconnects, SUDA software, developer tools, and years of optimization baked into every layer. Even as memory grows more critical, NVIDIA is the architect of the whole system, deciding how memory integrates, setting performance standards, owning the software layer. That structural power is real. Second, software is actively fighting back against the hardware bottleneck. Engineers are getting remarkably creative about reducing how much memory AI actually requires to run efficiently. An algorithm called FlashAttention rewrote how GPUs handle attention math. Processing data in smart tiles instead of reading the same giant matrices repeatedly, slashing memory traffic dramatically. Quantization is another weapon. Reducing numerical precision from 16-bit down to 4-bit means the same model fits in dramatically less memory, often with minimal quality loss on practical tasks. Stanford's AI Index confirmed. The cost of running a GPT 3.5 level system dropped over 280-fold between late 2022 and late 2024. Hardware costs falling 30% annually. Energy efficiency improving 40% per year. And then there's power. The IEA project's global data center electricity consumption will more than double, from 415 terawatt-hours in 2024 to roughly 945 terawatt-hours by 2030. Japan's entire electricity use. So the honest picture is this. Memory is a real bottleneck, especially for inference and agents, but software is fighting back fast, and power, cooling, land, grids, those are all stacking up too. The memory wall is real, but it isn't replacing compute as the one true bottleneck. It's joining a growing stack. Multiple constraints are compounding simultaneously. That's the actual story. Here's the big idea I want you to take away. We imagine AI as software, as thought, as intelligence. But the physical reality of what AI actually requires is something very, very different. Building state-of-the-art AI means acquiring training data, securing GPU clusters, sourcing HBM chips, contracting power grids, engineering cooling systems, constructing data centers on every continent. This is why AI isn't just a software story anymore. It's an energy story, a semiconductor story, a geopolitics story, a supply chain story. AI is physically embedded in the infrastructure of civilization itself. The history of AI is the history of bottlenecks. First, whoever had the data won. Then, whoever had the GPUs won. Now, it's about whoever can move information fast enough to keep those GPUs alive. The companies that shape AI's next chapter may not be the ones writing the cleverest code. They might be the ones building the fastest data highways. In memory fabs in South Korea and Idaho, AI does not just need a bigger brain, it needs a faster road. Next time you wait a second for an AI to respond, you'll know exactly what that small pause really represents. Maybe the most important question in tech isn't how smart can AI get? Maybe it's how fast can we move information? And who controls that road? That question is already reshaping the world. That's a wrap for today. The history of AI is a history of bottlenecks, and the next one is already here. So tell me, do you think this is an intelligence race or an infrastructure race?